So symbolic inversion, which is the theme of this week, is the um, endeavor to try to reconstruct exact mathematics from partial data. And one of the kinds of symbolic inversions we're going to look at is the situation where you have a floating point number, which is an approximation of a number that you think might be important, interesting, and you then want to reconstruct the exact number that this floating point number is an approximation of. And you can sort of see from the outset that what I'm saying here is not really mathematically well defined, but still, as I hope this example will show you, it sort of makes sense if you make some very modest assumptions on the numbers that you're talking about. And also, mathematics, even though this is not really a mathematically well-defined question, but still mathematics enters into how you solve a question of this type in a very strong way. So I'm going to do the following. You're going to have to take my word for this, but I'm generating a number. I'm running this a number of times so that I don't get a number that I've looked at before. I'm generating a random number which has a denominator that's somewhere between 1,000 and 4,000, and a numerator somewhere between 1,000 and 3,000. And I have no idea what it is other than that. But, and so this is hidden, this is saved in the variable secret that we will look at later after hopefully I've managed to guess what it is. But I'm giving myself as many digits of an approximation as I would like, and I think I want 1,000 digits. Right? So I'm asking Mabel to give me this approximation, and the question is, how do I reconstruct the rational number, the fraction, from the data that I have here? So one thing that you can sort of start out by doing is that you can try to rescale and hope to see some sort of pattern. And usually it helps a little bit if you can move things. I mean, I'm just rescaling the box a little bit, but the idea for doing this is that when I'm doing that, then my eyes will help me find these patterns that now are quite evident, right? So I have, for instance, 6, 1, 3, 2, 5, 9, 6, and I have it again down here, and I have it again down here, and so on. So this, of course, is not a surprise because it's a fraction. This is a fraction that I'm evaluating, so it's well known that the fraction, the floating point expansion of a fraction is going to be periodic. Right? So this is not surprising, but you can see this is in fact, the kind of thing that we're doing in visualization. By sort of rescaling the box, I could help myself to see what's going on. Now, I'm a little bit unsure if I have the shortest period. Of course, this might be sort of a repetition, but I think sort of looking superficially, I don't think that's the case. So I'm assuming now that we have some sort of repetition going on. And where does it start? Well, I mean, so it's a fairly long repetition that I'm seeing here. Just want to make sure that it doesn't seem to be repeated, but at least it goes on for a long time. And I don't know, maybe I could even do slightly better than this, but certainly this is something that's going to be repeated. And I'm trying to see if I can divide it over in smaller entities, but I don't think that's the case. I don't see any 7, 7 again before I see it again. If it's there, I don't see it. So, but anyway, it's not a problem if I repeat myself this way. Right? So what you see here is that I have some sort of beginning, and the beginning I chose was 92506069060, and then I have something which is repeated, and now it's basic elementary math to reconstruct the number like this, because of course, since I know that this is a repeated, this highlighted part is repeated infinitely often, I can just sort of put it in front of some appropriate power of 10, and then in front of another appropriate power of 10. And since these powers of 10 are systematic, they're 10 to the minus whatever the length is of the beginning, and then the length of the long thing, and then that's the first time, and then 10 to the minus whatever the length is of the beginning, then the long thing twice, and so on. And this is a geometric series that converges in a very straightforward way. So I'm going to ask for a little bit of help from Mabel to do this. Now, unfortunately, yeah, this happens again. There's something weird about Mabel that when I have marked this and asked to glue it in, then I get the whole thing, but I think I can do this by hand. So I'm going to remove the beginning of my fraction and call that the head, and then I'm keeping the tail until I have a repetition back at 7, 7, 3, 4, 0, and that is here. Right, so I'm going to remove all of this. So here's my head, here's my tail, and now I want to convince you that with this data I can reconstruct the number. Right, so I need to know how long these are. I just need to count the digits, but it's easier to ask Mabel for help. So I'm taking the common logarithm, the base 10 logarithm of head and tail, and so the period of the head is 9, and the period of the tail is 180. And then I'm claiming that if you compute this number here, which is, I put together the head and the tail, and I made an adjustment with the appropriate power of 10, then I get this number out. Right. So is that the correct number? Well, you can see that the difference between my secret number and what I computed is very small. So indeed, that looks quite promising. Right. So if I ask Mabel to clean this up for me, so I'm just taking this infinite sum, and I'm seeing what I get if I go. I mean, so here the approximation I did was I just took 2 copies of my tail. But of course, if I keep doing this, I get an infinite sum, and Mabel helps me compute what that is. It's this number here. So hopefully this was also what was in the secret number, and let's reveal it now. Oh yes, right. So you see what happened here was that I didn't do anything very impressive, even though it sort of feels good. So what I did was I took this random number. I knew that it was a fraction, so since it's a fraction, then the floating point approximation of it has some sort of periodicity. I saw that periodicity by rescaling. Then I took the data and cut it up in parts and reconstructed the data this way. So how much did I use for that? Well, I sort of needed about 189 digits of the original number. And then, of course, I also needed to see that I could repeat, that I found a repetition. So I guess I'm using another 180 to make sure that I'm seeing the right thing. Right. So, I mean, it's not a problem to give me 1,000 digits or 1,000,000 digits for something like this. So that's, I certainly have this data available, but I'll show you in a second that you can do this much more efficiently by using different kind of math. And this is really what's going to happen in this part of the course, that there's some mathematical tools that you could use to do the analysis of this kind of questions that is less known to you, I assume, and so I will spend time on them in the course. And so the one thing that is important here, and I'm going to have to rescale a little bit, is the idea of a continued fraction. So I'm taking my secret number, and I'm taking the approximation of the secret number. I mean, I know it now already, but I'm taking the approximation to the secret number as a continued fraction. So what is a continued fraction? Well, that's a way of writing a number as 1 over an integer plus 1 over another integer plus 1 over another integer, and so on. So all the data that you see out here to the left, this is the data that describes a number in this perhaps unusual way. right? So there's a huge number down here, and that's very important, but let's wait a little bit uh, before we address what's going on down there. Let me explain how you find these numbers here. That's actually extremely easy because the number that has to lie down here is chosen by taking essentially the reciprocals and rounding down. So I start with this number here, and I take the reciprocal. This is a number which is slightly bigger than 1, so when I round it down, I get 1. Then I subtract that. Then I get another number. I take the reciprocal of that, and I will get a number which is slightly bigger than 12. I will subtract 12, and I will keep going. This is called the Euclidean algorithm. And I keep on going, and the point is that if I have a rational number, then at some point this procedure will end. And if I have an irrational number, at some point this procedure will this procedure will never end, and we will have an infinite approximation. And this is what these mathematical objects are usually used at. You can find nice approximations of important constants by using these kinds of continued fractions. But what's going on down here? Well, what's going on down here is that this is actually an error. This number is not there because the rational number that I found has a continued fraction that ends right here. But of course, I'm doing things in approximation. I don't have the exact number. I only have an approximation of it. So there's going to be an error, right? And the point is that I was supposed to get a number which was supposed to be 0. Well, it's not 0, right? Because that's an error, but it's very close to 0. So when I take the reciprocal of it, I get a huge number. And this is the number that the Euclidean algorithm will find. So this gives us a way of reconstructing the data that I'm looking at in a very efficient way. I just keep on going until I get a huge number. So what do I mean by huge number? That's not mathematically well defined, but we can sort of use a trial and error approach to this. So what's going on is, I mean, this is perhaps an easier way of seeing what's going on. I will create the nth convergence, which is what you get by, that's the name for what you get by taking the first number here, that's 1. You take the second number here and then you stop, that's 12 over 13. You keep on going with 2 and so on. And you can see this sort of goes on rather slowly until it explodes down here. Right? Why does it explode? Well, it explodes because of this number, which is an indicator that, in fact, we are done with the approximation. So what the algorithm I'm proposing here is that you sort of do the Euclidean algorithm, you get better and better approximations until you get something which is too big, and then you go back and look before. Right? And the point is that this works at other kinds of precision as well. We could use 1,000 digits like I had before. Then if I have 1,000 digits, when this explodes, it's going to explode even more because the error I have is much smaller, so the reciprocal is much bigger. And you can see this explodes in an enormous number up here. And again, the step just before it explodes, that's what I'm looking for, right? I could do this with 15 digits. Then I would get the number that I'm looking for. And so you can see this is much, much more efficient than what I did before because I don't need several hundred digits. I just need 15. Right? Actually, we can see how much I can squeeze this. If I go down to 12, it still works. If I go down to 10, it still works. I think I'm pushing it here. If I go down to 7, well, it actually works. But so I still get the right approximation. So now I have so few digits that I can't be sure of that. And also, it's a little bit hard to say that this is much worse than the other one. So I mean, I'm not really claiming that you could do this with 7 digits, but certainly with 15, there's something dramatic going on in this step, which gives me an indication that what I have here is correct. Right. So what happened here was that I showed you how to use the math of the continued fraction to answer the question, which is not really mathematically well defined. What is this number? Right? I'm saying I have an approximation. So essentially, I'm saying I have an interval, a small interval, which explains. I mean, that's sort of the interval of numbers that are rounded off to this floating point number I have. Of course, in that interval, there's lots and lots of interesting numbers, and we decide to find precisely this one.